Hi everyone, I'm Atharva Saranke and I'm presenting today with my teammate Vishal Pednekar. Our project is called No Role Contendere and it's all about a hidden problem in software security, that is cryptographic API misuse. Developers might not be writing their own crypto anymore, which is good, but using a library incorrectly is just as dangerous. So we built a Python-based analyzer that can detect crypto misuses even when they are buried across multiple functions. And today, we're going to show you why that matters, how it works, and where it's already been caught in the wild. Because even if you're not rolling your own crypto, what happens when you roll it wrong with the right tools? The crypto API trap. So, what's the actual problem? Developers are told not to build their own cryptography, so they turn to libraries like OpenSSL or PyCryptoDome, which is the library we analyzed in this project. That sounds like the right move, right? But here's the trap. These libraries are complex and incredibly easy to misuse. Using them wrong is like trying to assemble a rocket with IKEA instructions. All the parts are there, but the risks are massive. If you miss a step, you might think your data is secure because it's encrypted. But if you're using ECB mode or you forgot to add an IV, that encryption is just practically useless. These aren't rare or advanced bugs. They're subtle, common misuses, and they're everywhere. Part of the issue is that crypto libraries don't throw errors when you use them insecurely. They do exactly what you tell them, even if it weakens security. You can pass a hard coded key, skip the salt in a key derivation function, or choose the wrong encryption mode, and the program still runs. There is no error, no red flag. But under the hood, it's vulnerable. That's what makes these kind of bugs especially dangerous. They are silent. They don't crash the app or cause a syntax error, but they quietly compromise your data security. And once this code goes into production, the damage can be hard to reverse. In a way, cryptographic API misuse is the perfect example of a high impact, low visibility bug. You won't notice it unless you are explicitly looking for it. And that's exactly the gap our project is designed to fill. Here are some of the most common mistakes developers make when working with cryptographic APIs and the ones our tool is built to detect. First, we have hard coded keys. These are encryption keys written directly in the source code, usually as string literals. If that code gets pushed to a public GitHub repository, the key is no longer a secret. It's like locking your front door and taping the key to it. Next, we often see developers using AES in ECB mode. ECB stands for Electronic Codebook and it's the simplest mode of encryption. But the problem is, it's deterministic. That means the same input will always produce the same encrypted output. It doesn't randomize the ciphertext at all, which makes it easy to spot patterns and leak information. Another issue is missing IVs or initialization vectors. These are random values that should be added when using modes like CBC or CFP. Without an IV, even a strong encryption algorithm can become predictable. It's like sending the same message with the same envelope every time. And finally, we have static salts in PBKDF2. PBKDF2 stands for password based key derivation function. It's a way to turn a password into a secure cryptographic key, and it needs a salt, which is just a random string added to make each output unique. But if that salt is reused, attackers can pre compute hashes and run rainbow table attacks to crack passwords efficiently. These aren't theoretical issues, we have seen them in the real world. Let's take a look at what happens when this goes wrong in the real world. Back in 2013, Adobe had a massive breach. Over 150 million users were affected, and one of the core issues was how they stored passwords. They didn't hash them, instead, they used triple DES in ECB mode to encrypt them. So, if two people had the same password, it produced the same ciphertext. Attackers didn't need to break the encryption, they could just compare the patterns and reverse the most common passwords like 123456 or the term password. And because people reuse passwords across sites, The damage spread far beyond Adobe. They face lawsuits and a massive hit to their reputation, all from using cryptographic libraries the wrong way. Now, these mistakes aren't always obvious. You might define a key in one function, pass it to another, and only use it in the third one. And that's totally valid code, but it's hard to track. Most linters only analyze one function at a time, so they'll miss a misuse unless it happens in the same place the value is defined. That's where we come in. Our analyzer performs interprocedural analysis. That means we follow the trail across multiple functions, even if the misuse only shows up at the very end of the call chain. Once we realized that crypto misuse often isn't local to a single function, we needed a way to track how values move across the program. So we started with Python's abstract syntax tree, or AST. The AST breaks down code into its core structure, which we can walk through programmatically. Using the AST, we trace function definitions, keep track of how variables are assigned and passed around, and watch for specific crypto API calls. More importantly, we follow these values across function boundaries. So even if a key is defined in one function and misused several calls later, we still catch it. This lets us detect classic misuses like hard-coded keys, insecure modes like ECB, or missing IVs even when the code looks clean on the surface. So how does the tool actually work? It starts by walking the AST function by function. To understand how the code is structured, we track function calls and their arguments to see how values are passed around. Then we build a reverse call graph which lets us trace back where those arguments originated from. Once we have that structure in place, we check for insecure patterns like the use of ECB modes, missing IVs or hard-coded secrets. What makes this powerful is that we are not relying on simple string matching or linting rules. We're performing static analysis that actually understands the logic of the program and how data moves through it. Our analyzer works like a forensic detective. It doesn't just examine the crime scene, it traces the fingerprints back to where the suspect first entered the building. Misuse cryptography doesn't just exist in theory, it shows up in real applications and the impact is serious. These bugs can leak user data as seen with Adobe, expose login credentials, and make encryption meaningless. The worst part, they often go unnoticed because they are buried deep in logic, not syntax errors. And once a repo is public or deployed, attackers don't need fancy exploits. They just need to read the source code. Our tool is designed to stop that from happening, to find these bugs early before they become headlines. So, that was an overview of the problem and our solution. Up next, Vishal will walk you through the actual code implementation of our analyzer. He'll show you how we designed the crypto analyzer class and give a quick demo of the tool analyzing real repositories. You'll get to see exactly how the misuses are caught in practice.
Alright, let's dive into the tool I have built. This Python script is designed to analyze other Python files and more specifically to look for misuses of cryptographic APIs, like using weak encryption modes or hard-coded keys and salts. We are focusing on the PyCryptodome library, which is a commonly used crypto library in Python. Things like using AES in ECB mode or forgetting to add an initialization vector in CBC mode. These are subtle mistakes that can make encryption totally insecure, and they often go unnoticed in code reviews. So this tool uses static analysis, meaning it does not run the code, it just reads and interprets the code structure to find these mistakes. That's where the next piece comes in, the AST. What is AST and why we are using it? AST stands for Abstract Syntax Tree. Think of it like a blueprint or a map of your Python code. So when you write code, you think in terms of variables, loops, functions, etc. The Python interpreter behind the scenes actually parses that code into a structured format, that is a tree, where each node represents something like a function call, an assignment, a constant, and so on. By using Python's built-in AST module, we can tap into this representation, That way, instead of searching for insecure patterns using fragile regex or line-by-line scanning, we are directly looking at the syntactic building blocks of the code. That's powerful because it's safe. We don't need to execute any untrusted code, and it's accurate because we are seeing exactly how the code is structured, just like Python sees it. So in this project, I have subclass ast.nodeVisitor, which lets me walk through this tree and customize how I handle things like functions, assignments, and calls. Now let's talk about the core of this tool, that is the CryptoAnalyzer class. This is a class that inherits from the ast.nodeVisitor, and it handles all the logic for tracking variables, detecting risky API usage, and even tracing how data flow across function boundaries. So this is the constructor of the CryptoAnalyzer class, and within this I have set up several dictionaries and lists. The first one with the hard-coded keys. This stores variables that are set to string or byte values, which are likely hard-coded secrets. The second is function defs. This keeps track of all function definitions. The issues list is going to store all the issues that are encountered in our different Python files. Fourth is the call graph. This is where I will map which functions are calling which is critical for interprocedural analysis. And then last one is the current function, which just keeps track of which function I'm currently analyzing. The first function that's going to be called within here is visit function def. When I see a function definition, I store it in function def, which is this variable right here, so I can analyze or revisit it later. I also update the current function so I know where I am in the call graph. The second function that we are going to look at is the visit assign. So if there's a variable being assigned a constant like a string or bytes literal, I log it as a hard-coded key or sort. This is stored with its variable name and the line number right in the hard-coded keys dictionary. Okay, so let's move on to our next function, that is the visit call. And this is a big one. So let's understand step by step what's going on over here. For every function call, I'm going to first figure out the function's name, track which function is calling which. I'm going to build a call graph right here. And then if the call is to aes.new or pbkdf2, I hand it off to another method to check if it's being used securely. So it's called check AES usage and check pbkdf2 usage respectively. Let's go to track function call. It's very simple. Like if the function is not in the call graph, I'm just going to add it to the call graph. That's about it. Get the call function name. It's just going to use the AST module to get the function name and return its ID back to our caller function. After visiting all the functions, I run a method called traceDataFlow. So here's what it does. Sometimes a value like a key or sort is not hard-coded in the same function that uses AES or PBKDF2. It might be passed down through one or more function calls. This is what's called interprocedural data flow. What I do is build a reverse call graph, meaning for each function I figure out who called it. Then for every sensitive crypto API call I try to trace where its arguments came from using the trace argument source, which is another function that's defined right here. If I eventually find out that a key or sort was originally hard-coded in another function, I log it as a security issue. Now let's look at the checks specific to the two cryptographic APIs we care about. So the first one is the check AES usage. So I'm quickly going to scroll over to that function. This method checks if AES.new method is being used with mode ECB, which is considered insecure. If it's using CBC or CFB modes, it makes sure an initialization vector is provided, because without that, even those modes can become insecure. It also checks if the key being passed is one we previously marked as hard-coded. Now let's move on to check PBKDF2 usage, which is our next function right here. It looks huge, but actually it's not. It's very simple. So here I look at the sort argument to PBKDF2. I check if the sort is none which is insecure, a hard-coded string or bytes. So it's going to be this line or a variable that was previously assigned a hard-coded value. So it's going to be that. So this function covers both positional as well as keyword arguments. The first if block covers all the positional arguments and the second block covers all the keyword arguments. So both of them are covered if there's an insecurity that needs to be reported. And then finally there's the report method. The report method just compiles all the issues I found and returns them as a list of dictionaries, each with the line number and a description of the problem. It sorts them by line number to keep the output clean and readable. So outside the class, I have three more functions. The first one is the analyze file, which reads the contents of one Python file, builds its AST, and runs our analyzer on it. The second is the analyze path. This one's a bit smarter. It can either handle a single file or recursively go through a directory and analyze every .py file it finds. And last is the main function. This is the entry point of the script. It takes in command line arguments, passes them to the analyze path function, and finally prints out the results in formatted JSON. So just to recap what we have spoken over here, we are using the AST module to safely and accurately analyze Python code. We are identifying insecure cryptographic usage patterns in PyCryptodome. And we are doing this not just within one function, but across multiple function calls, thanks to interprocedural analysis using a call graph. This kind of tool is super useful for security auditing, especially in large code bases where crypto misuses are hard to spot manually. Now that we know how the code works, let's test it against some test cases. I have written about 8 test cases to test various functionality of the script. First, I'm going to run it through PyTest and see if we pass all those test cases. So here we are in the terminal, and then I have this file for PyTest, and I have written all the test cases over here. For example, I want to test the pbkdf2 with sort file, and I'm just going to check if it doesn't have any issues or whether if it has any issues in case of no sort. Let's try to run this, and when we run it, we can see that all 8 tests has been passed. Let's look at the results individually. I'm going to run our analysis file, that is the original file, that is the API misuse checker.py, against all those test cases. Coming back to the terminal, there we go, and here we can see which test cases have vulnerability and which do not. Let's quickly take a look at few of them. Here we have test pbkdf2 with no sort, and it is producing a vulnerability which is pbkdf2 used with none as sort. We can also verify these from the test cases. So if we go to this file over here with no sort, we can see that the sort here was none, and this is insecure. We can also see that there's another file which has hard-coded sort, and even that file is going to produce a vulnerability right here used with hard-coded sort, and also says the variable name which was sort. So this is the variable name sort which has the hard-coded string, and it is being used with the pbkdf2 method. So now let's take a look at how we use this code to find vulnerabilities in some public repositories on GitHub. Okay, so I have these three GitHub repositories. These are publicly available. So the first one is from Google. It's called Python Diamond, and it's got one diamond folder, and then it's got a init.py and a setup.py. So if we inspect this file, we will see that there is this vulnerability on line number 30. So this one is using the AES new method, and then it is using it in the ECB mode, which is deemed to be insecure. Let's see if our script is able to catch this and report it back to us. The second one that we are going to see is the image encryption. This is from user 163, and it's got one Python file. Yeah, it's got this one Python file. It's pyenc.py, and yeah, it's using the pycryptodome library, and I can see some aes.cbc mode, but I'm just not sure what other thing it may have, what vulnerability it may have. So let's see if our tool is able to show it to us. And the last one is the insta followback, and this is from, I don't know how to read this. It's MQTT-H3W. Okay, so it's probably something for Matteo Giovannetti. I don't know. I'm not gonna pronounce this. Uh, okay, so I'm going to run each of these three repositories through my script, and let's find out. So here I'm on the terminal, and I'm already in the analysis tool folder, and I'm going to run this command. So let's first check the Python daemon repository. So how I'm going to run this is Python 3 API misuse checker.py, and then I will provide a path to the folder. So I'm going to pass the entire folder to the program and see what happens. So when I run this, we can see setup.py has no vulnerabilities, but here in init.py, it shows that on line number 30, an insecure AES mode has been detected. So just as we expected, the ECB mode is deemed to be insecure and it's being reported perfectly fine. Let's check out the second repository, which was the image encryption. Oh well, it has little more vulnerabilities. So the first one is on line 46 that an ECB mode is detected, and then it's on line 83 again the AES ECB mode has been detected. So let's go to pymgenc.py and verify this. So here, this is the pymgenc.py, and then it says line number 46 and line number 83. So let's scroll down to line number 46, and yes, so what it is doing here is probably it's trying to do it with aes.cbc mode. Um, but the thing is, so if the mode is set to aes.cbc, it's going to do this. But if it is set to something else, or it is just not set to aes.cbc mode, it is just going to fall back to the ECB mode, which is going to be insecure in this case. So let's look at line number 83, and yes, it's the same issue over here. Let's move on to our third repository, and that is going to be the insta followback, and it's got a lot of issues in this. So the insta followback gui.py, this file has got 4 issues. Then there are 2 more files which don't have any issues, and then there's another file which is called instafollowback.py. It's got another 4 issues. So this is like hard-coded key used in aes.new. So this is new. So we already looked at aes.ecb mode in the previous 2 repositories. Let's look at line number 34 in insta followback GUI. So here it is in GUI.py, and then we are looking at line number 34. So right here, it's using ECB mode, and then it is using this key32 variable, and here we have, this is a hard-coded value right here, and our script is able to detect this perfectly, which is great. Manually, it would have taken someone a few hours to maybe identify these things. They had to go through each and every line, and maybe they wouldn't have even recognized this. So If they are reading it like that, they would just see AES.new key32 and probably not even realize that the variable key32 might be hard coded. So using the script, we very easily analyzed three different repositories on GitHub and found out that they have some issues with them. So this just makes our work much more easier. Isn't that great? We have designed the script in such a way that even if we have a large Python project, which is going to have a lot of subdirectories, and each subdirectory will have multiple Python files, and let's say each of those Python files is going to have some kind of vulnerability with respect to the PyCryptodome APIs, our script is going to detect them and report them accordingly. So for this, I have the original three GitHub repositories that we tested our script with, and then I have also added one more repository from GitHub. It's called the Steganograph. Yeah, right here. So it's called the Steganography repository from Piccolino 1965, and it's got another file in it. So I have just added this one with all others. So I'm just going to show you the repositories. It's gonna be here in real world tests. And if I listen to this, I'm sorry. Okay. So we got four different GitHub repositories within the real world test folder, and we can scan the vulnerabilities in all the four repositories all at the same time. So for this, I'm gonna go back to my analysis tool and I'm going to run Python 3 API message checker.py, and then I'm just going to provide a directory path to real world tests. That's it. Hit enter, and there we go. So steganography, it's got a vulnerability on line 19. There's a missing initialization vector in the CBC mode. Then we got the insta follow back. We got those same three vulnerabilities. And yeah, so whatever vulnerabilities we saw in the past in the previous three repositories, all those are here. And then we also got the vulnerabilities in the steganography repository. So this is great, like emulating a huge project and finding the vulnerabilities in that. That's all from my side. Over to Atharva.
Thank you, Vishal. To wrap things up, let's quickly go over the key takeaways from our project. First, even though developers are using standard crypto libraries like PyCryptodome, they are still making dangerous mistakes. These misuses often span multiple functions and can easily go unnoticed with traditional tools. Our tool addresses that by using static analysis and the AST to trace crypto API usage across an entire Python program. It flags misuses like ECB mode, missing IVs, hard-coded keys, and static solves, even if the misuse is several function calls deep. Looking ahead, we can expand this tool in a few exciting directions. One possibility is to support additional libraries like OpenSSL in C or the cryptography package in Python. We can also explore detecting more complex issues around custom key management or insecure randomness. Another step forward could be turning this into a GitHub action so it can automatically analyze pull requests and flag crypto misuse before the code is merged. We can even look at integrating it into IDEs like VS Code to give developers real time feedback as they write. Ultimately, our goal is to make secure cryptographic usage not just easier but automatic. Thank you for watching our presentation. We started with the question, what happens when developers roll it wrong, even when using the right tools? Through this project, we showed that cryptographic API misuse is not rare, it's just rarely detected. Our analyzer finds those subtle, scattered misuses that traditional tools miss and helps make security a built in part of writing code, not an afterthought. We are excited about where this tool can go next, and we'd love to hear your thoughts, ideas, or feedback. Thank you.